Thanks. Thanks, Ken. Thanks for this invitation. It's actually going to be a lot of fun to have this like in a small forum because my talk is sort of built for 4.5 hours, and I'm going to dive in different places to it. And I always try to see within the first 10 minutes what people are interested in, and then I'm going to kind of like doing the accordion method of expanding and contracting topics. So this can be super like interactive. I'm happy to elaborate on things that you find interesting, and I'm happy to try to get a sense of what your main background interests are. So, how many here are from engineering? 3, 4. How many are from social sciences, humanities, computer science? Okay, so engineering, computer science. Okay. So as Ken said, I'm at Cornell right now. This is a view from campus on our beautiful Ithaca, New York, up in the woodlands. This is from actually a photo I took from my commute up to campus. But very soon it's going to be looking like this for a while. And this is why people have a lot of time to be caved them in their labs and do research. My research is grounded in my amazing graduate students here in order of seniority, or first in, first out order of graduation. So I've been there for 4 years. And my research studies human-robot collaboration, which I think about more as sort of the workplace interaction between humans and robots, and human-robot companionship, which is broadly speaking the home interaction between humans and robots. As of late, I have a lab mission. I was at a talk by Danielle Wood, and she's an interesting researcher at MIT who studies the relationship between society and space policy. And she said, this is the mission of my lab. I'm like, how come I don't have a mission for my lab? So I spent some time and I thought, what would be the mission for our labs? And I think it's actually really important since I felt like this is something I wanted to put to words. And it's really to understand the complex interplay between human behaviors, attitudes, and needs, and personal robotic technologies in order to design robots that best support human values. We have a methodology. Our methodology is sort of split into 3 pretty separate but interacting topics. We study a lot of AI for human-robot collaboration and companionship. We do design of robotic systems. So we design robots from the ground up. And we are very active in the sort of design community. And most of my talk is actually planned to be about how we connect AI with design. In what I currently consider, and I'm not supposed to play favorites with my projects in the lab, but the most interesting project in my lab. So I'm going to spend a lot of time on this because I feel like it's the big idea that interests me right now. And then I've done this lesson since I'm coming to Cornell, but I've spent quite a few years on sort of studying human-machine interaction from an experimental and empirical setting. So we had lab studies, field studies. It made me into somewhat of an experimental method snob, which comes in handy when I review papers because it's very quick to review papers. I'm just like, there's no research question in this paper. I was interested for many years in the topic of fluency, and this and so the latest big project was just completed, and I feel like it's sort of like a cycle. Fluency to me is this sense of everything just gelling. You know, everybody's doing their part at the right time, and it's this ephemeral feeling that you know when it happens. So I love watching pit stops. I don't like watching races, but the pit stops are amazing. So my dream since my first year of my PhD is if I can make a robot that works like a pit stop operator, this is sort of where I look for the next like 40 years of my life, and starting 15 years ago when I started my PhD. It's not just for highly trained professionals. I took this video from a rooftop in New York. Here you can see a demolition team, and you can see the high fluency part of the team and the low fluency part of the team. And start looking at the high fluency part first, and then see how the low fluency part is not fluent. So here, the high fluency part, you know, things are just moving along. But then look at what's going on here. So you have this person. He's like, I don't know, put this here. This person goes, comes back, and something is wrong with this team here. And what I would say is that the fluency is wrong. So I'm not going to talk much about this because these are quite old projects, but I tried to formally model this in a Markov decision process with 2 agents and looked at whether sort of taking risks on the robot's part could improve fluency. And then at some point I spent some time on these more sort of connectivist network ideas that were based on research that just came out at the time that tried to study how human brains work when they collaborate and how they achieve a high level of fluency. And there I started first to think about these ideas of having rhythm as part of the model and having these ideas of sort of being able to retract your actions halfway. And as part of this work, I spent quite a bit on these ideas of fluency metrics. How do we measure fluency? And a fortunate or unfortunate aspect of these is that I suggested some metrics, and these have sort of caught on quite successfully in the human-robot collaboration literature. But this method, I felt a little bit guilty about it most of the time because these metrics were just ideas that I put in at the end of a paper. I was like, maybe we should measure these things. They could measure fluency. And then people are like, oh, but there's a metric. Because one of the problems you have in human-robot interaction, I would say as a general statement, is we don't have good benchmarks and metrics. I think in robotics, we're kind of like halfway. And sometimes there's the computer vision envy, where they have these like very clear benchmarks and metrics. But I think computer vision has the wrong metrics, in my opinion, but that's another talk. But we don't have a good sense of like what is a successful human-robot interaction. And so I suggested these measures, and I've spent a few years, and this was just published a couple of months ago, of just trying to see how these metrics behave in different situations. So if you're interested in fluency and just in the question of how do we measure things, this paper, which has been a little bit of a pet project of mine, which I've done on like once a while on weekends and late nights, was trying to simulate different interactions and measuring these metrics and looking at them almost like as dynamics, like looking at the dynamics of how these metrics change as the team changes strategies. So this is just a little. So here's one metric is like how much is the human idle? So a lot of people use this metric. Actually, the metric that's most used is this functional delay, which is a metric I suggested, which is the time between the end of the human's action and the beginning of the robot's action. And you measure this often as a ratio of the overall task time. And then people say, okay, we reduce functional delay by 20% by adding a neural network. And so people look at this and they say, okay, functional delay, there's an intuition. So these are our intuitive metrics. This is human idle time. How much does the human do nothing? Robot idle time, functional delay, and then concurrent activity. How much do people, concurrent activity came from my own research that showed that when this went up, people thought the team was performing much better. It's this thing like when you are, like imagine you're washing dishes and your partner is watching TV versus you're washing dishes and your partner is cleaning the cabinet, and you feel like the team is working together, even though maybe the whole amount of time it wouldn't be different. So we showed that if the concurrent activity would be low, people thought the team was not working well together. Whereas if they would have the same amount of idle time, but they would be idle together, this seemed to people to be a better team situation. So this is what these all came from my observations of looking at studies in my lab. And we were saying, okay, can we correlate this with people's satisfaction? And this was always very high. So then I said, okay, let's see, let's create these different simulations of different kinds of humans and robots and different strategies that they can behave and see. And one of the things that I showed that these metrics have this ring to them. So if you measure them after only like 10 rounds, you might just be accidentally be on the low end of these metrics because it takes time for them to settle. So one of the insights from this work was that you have to kind of like figure out what is the settling time of these metrics in terms of the turn length of the human and the robot. So this is what you were asking? Yeah.
Another impact on fluency is that a lot of research shows that the more effort something seems to take, the higher people value the results. So counterintuitively, if it's easy for something to happen more fluent, then they perceive less value in what's occurring.
Yeah, so like a parent effort. I think that makes sense. So I try to really look at this in the most naive way. So in a way that can we put a sensor on the team and say this is a high fluency team and this is a low fluency team, without asking people. So I wanted to really, I kind of like said, okay, all we have here is actions. An action starts and action ends, and it can overlap or not overlap. So I wanted to like boil it down to the sort of bare minimum. Yeah, and especially since these metrics have been, I think again, I can't complain because people cite my metrics paper, but it wasn't a metrics paper, it was just a paper on something else. And so I feel like I like to be cautious when we talk about what we are actually achieving. And I think, and unfortunately this obviously has no funding and will never have funding. And so this is, but I always say in the community, I say let's talk about like how do we measure our success. I think that's a big question that's so under discussed overall in the robotics community. Like how do we know that something is good and what are we like what is good and this is just my own maybe a corner of this. As Ken said, I spent a couple of years looking at joint musicianship. I was most interesting. So I wasn't very interested in music, but I was interested in music as like a very high stakes and very high sensitivity collaborative scenario. And I just want to briefly say that there's I looked mostly at this idea again of fluency between two musicians and trying to model. So you kind of had to model both the perception and the dynamics of the musician and the musical interaction. I prefer not to spend much more time on this. So right now, in terms of sort of the AI aspect of our lab, we've been looking a lot at looking at formal methods for human-robot interaction. This is a collaboration with Hadas Kres-Gazit. So formal methods is it's sort of a branch of robotics that is very heavily embedded in formal logic. And formal method verification has huge successes in electronics circuit design and also in other cyber physical systems like controllers for autonomous vehicles and airplane fault mode. So we were trying to think, and we have been thinking for the last 3 years or so, can we have a framework of formal methods for human-robot interaction? What would that look like? And this is kind of our overall approach where we have a human and sort of think about a delivery driver trying to have like a last 50-meter robot that does the final delivery for them. And they specify the controller using high-level requirements such as natural language. So saying something like, never wait more than 2 minutes, don't get closer to a person than 10 centimeters, etc. So they have some high-level ideas of what they want the robot to do. And then we're translating this into formal logic statements. And we're using a synthesis that automatically synthesizes a controller that is guaranteed to either be within the specifications given to the robot or stop and say why it can't do what it's asked to do. So this also connects a little bit to this idea of explainable controllers. And the big problem here is, of course, the human model, right? Because to be able to synthesize a controller automatically from specifications, you have to make some assumption about the humans. And we've started to implement this, and this is kind of like almost future work. So we don't have a lot of results on this yet. We've started to work on this idea of using sort of hand-coded human models that then are then updated through human behavior data sets. So for example, we have a data set of I think about 10,000 handovers with motion trajectories. And then we're using this human model to see if we can actually build a robot that can satisfy certain specifications. We have 2 papers on this out so far. We did one experiment with this sort of one implementation of using formal logic to create a robotic controller that stays close enough to a person. So again, think about an autonomous robot that holds an IV for a patient, but also it doesn't get too close and is able to navigate. And the latest paper that was just at IROS, I think last week or next week? Coming up. It's going to be at IROS. Is how do we formally specify this problem of handing over an object from a human to a robot? And I think this is super promising. It's another one of those. Overall, my approach is to try to solve problems that I know that I can't solve, but hopefully learn something interesting. This is also why I said that if it fails 50% of the time, there's a lot of interesting things to learn from why it fails. And I think here we've been able to create a single controller, so a single synthesizer that can create all of the classic handover controllers that have been out in HRI just with the same software. You just change the specification. So you change something about the timing that you want, and then you get a certain behavior from the handover controller. So this is going to be in ICRA next week, in IROS next week. All right. The second third of my lab's research, and this was mostly while I was in Israel, has to do with these studies of human-robot interaction. Here, a lot of this will be harking back in my evening talk about social robots and their role in society. But some of this work, this was sort of the longest running study where we looked at a robot giving people emotional feedback when they disclose traumatic events to the robot. So we studied this actually for several years. It's one of the, I would say, the largest HRI studies. It was over 300 participants, each one spending over an hour with the robot. And we looked at how a robot, for example, can give sort of positive or negative responsive feedback to make people feel heard when they share something traumatic. We looked at robots that help with couples conflict, and each of these have interesting lessons. I'm happy to expand on any of them if this is particularly interesting to somebody. And then we spend quite a few years on looking at robot presence and how it changes humans' compliance in situations where you would like to, for example, not have people take cookies from a seminar. But I want to talk about the latest study, which is a collaboration with an economist. And this was actually the first, and this was also sort of surprising, the first human-robot interaction study that used real economics models and used real compensation for people. And we talked to some economists that are involved in like labor policy, and we said, okay, what is really interesting from an economics perspective in human-robot interaction? And so they said, well, we would be really interested to see whether people change their behavior based on the robot's behavior if they have to work for something, just work for monetary incentives. And so we made this very boring task that was literally it was literally defined as having no intrinsic motivation to it. So it should be as boring and as possible. You can't get better at it, and you get paid a certain amount for every task that you complete. And then we had the robot do the same task right next to you, and you get paid based on the difference between you and the robot. So if the robot does better than you, then you get paid less. If the robot and think about you're working at a checkout at, I don't know, at Whole Foods or Trader Joe's or Giant Eagle, and you have an automatic checkout next to you. And you're not really competing, but you're kind of competing. Another example would be a future where you have sort of like a mixed fleet of autonomous and human drivers, and the amount of money you walk home with at the end is dependent on how much better you are or how much faster you are compared to the automatic. And so economic theory predicts that due to a kind of a complicated effect, which is actually super interesting. So if you're interested in this, read the paper. The economics part of it is also fascinating, but economic theory, especially sort of looking at advances that have been done in the last 10 years, show that the robot's increased performance should decrease your own performance, even though you get paid the same amount for every task you do. So you do this for half an hour, you get paid 10 cents for every one you complete. You shouldn't care. But if the robot, and we found the same effect, you can see here, the robot scores negatively predicts with a very high significance a decrease of the person's score by about 10%. And obviously the people like the robot less. Interestingly, people also think that they're worse at the task when the robot is better. So there's this like peer comparison effect that we found. And the last thing, which is sort of more anecdotal, is actually the worse people are, the better think that they are at this task, which is maybe like a more general human failure. But this is sort of like the first of two studies we did. We did another study showing that most of these effects reverse when the robot's performance adds to your payment. So you actually work harder when the robot works harder. And I think this has really interesting repercussions for how do we structure these like human-robot workplaces in terms of the compensation of what people, like should people think about the robots as their competitors or their collaborators, and how do we incentivize people's performance within a sort of a hybrid workforce. And again, it's a little bit still out into the future, but it's a project I really enjoy, and I really enjoy the kind of discussion we have, because the things that economists think about are very different than things that roboticists think about, and this has always been a great opportunities for collaboration. So now to like a little bit of a longer chapter, and this is a project that's been going on for several years, and we just got renewed on a grant, so I'm really happy about this. So we have another few years to think about this. And this is the idea of human-robot collaborative design. And the vision is right here. You have a person that's designing something. So here, let's say this is a model of the new iPhone. And you have a designer sitting there and trying to figure out the components and how the systems connect to each other. And this is designed sort of more from the engineering design perspective, but we also have an example of architecture, restaurant design, race car design, and the last one I'm going to show soon is voting district design. And I don't know if California is at all contested in terms of gerrymandering, but a lot of states are. So we look at this problem of like, how do you make the most fair voting districts? But basically, we have a problem that is a design problem. Design problems are different from physical problems, because design problems are usually trade-off problems. So you don't have clear optimal points in this design task. Second, people's preferences change as they're learning about design tasks. So there's a learning trajectory within the process of solving the problem. They're usually high dimensional to an extent that you can't search them efficiently. And so can we make robots that can help designers? And what does it even mean to help a designer with AI? But the idea, like, why do we want human-robot collaborative design? First of all, our industry is mostly moving towards research and design. So if we want to think about the future workforce, factory assembly might not be the right kind of place to invest, because 90% of the value generated in the US in product generation is in the research and design process. Second, humans and AI are actually really good counterparts in design, because people are very good at intuition. Like, you see something and you're immediately like, oh, this is obviously a bad idea. I don't know why, but nobody would put like a pizza oven in a sushi restaurant. So we have like a restaurant design problem. And no human would ever say that you want to put a pizza oven in a sushi restaurant, right? We generalize very quickly from examples, but people are good at number crunching. People don't have cognitive bias. For example, designers love their first idea, and usually it sticks. And then we also want to, we think robots are a good idea because decades and centuries of design and knowledge and research have shown that using physical models is imperative to create good design. So no architect will ever go just from like CAD to building. Like, you build a model, and this idea of a tangible representation, and there's, again, decades of research on this that shows it enhances creativity, collaboration, problem solving, etc. So how do we model this problem? Let's look at an office layout problem. This is a problem that Autodesk has been really grappling with for a few years, and if anybody has an inner Autodesk, I think they should fund this project, but they're not. So Autodesk cares about this project a lot. And they give an example of having, you want to lay out an office. So let's say you're moving to a new lab, and you have to decide now, this is a design problem. You have to decide, you're moving to a new lab. How many tables do you buy? Where do you put them? And so any solution is some vector or some representation. And for us, it will be, let's say we have a set of tables we can buy from, so we can have an x, y coordinate for each of the tables, and this would be a solution. And then you have objectives. The objective could be that you want people to have enough space, that some people like quiet places, some people like loud places. You want to have daylight, reaching everybody to the same amount. And so you have something in the objective space, and then you need to have some model that translates every solution. And this is usually done using simulations. And this is usually a pretty solved problem in most problems that we deal with. Like, going from your solution space to the objective space is usually not fast, but it's determined. The problem is the solution space is huge. Like, even just putting tables in a lab, the solution space is huge, depending also what resolution you want to have the solution space. So people are not good at finding a good solution, and AI search is not very useful, and this has been shown. Again, there's actually a lot of research on design space exploration in relation to search, and AI is not good at searching this. The best the community is doing is genetic algorithms. So this is currently the state of the art of being able to find good solutions for design problems is genetic algorithm search. So we're suggesting this idea of having this human in the loop kind of idea. We have a human designer. It can do higher level decisions. It can explore the space, and it can see what the outcomes is, like what the objective space looks like in some kind of visualization that's hopefully useful. It can ask the AI for certain explanations about the solution space or the objective space. And the machine provides the data mining, search, model evaluation. The first study we did was not with a robot yet, so we just built this tangible interface where we can track all the movements that people do on the table. And we had the AI basically search around previous solutions that the person did. So it's a very, I wouldn't even call it AI. It was basically like a local search agent. All it did was it waited for a few minutes and then was trying to look for solutions that are close in some way to a solution that the person was interested in. So this was the first, and here's a characteristic user from our system. So this was in a study we did. The problem we try to solve here is a satellite design problem. This is the cost, so we want it to be as low as possible, and this is the science benefit of the particular satellite. So this is how good it is between 0 and 1, so we can go up to like 25% benefit of the satellite design. And we can see that people search quite narrowly. So their solution space, so each dot here is one solution plotted onto the cost-benefit trade-off. Does this graph make sense? Or is there any questions about this graph? And so they did 3 rounds of 10 minutes each. I think it was 10 minutes in this. And you can see the humans searching the design space. They can get to kind of like a linear trade-off, and they stay pretty narrow on this. So they can add more features, but it costs them more money. AI has a sort of like more distributed search space, and this is like 10 minutes of AI search. And it gets to, it's hard to say, you can say that these solutions dominate the AI solutions because they're very cheap and they can get to pretty good. So the AI doesn't get to these like really cheap and okay solutions. But when we do this like local search around the human's suggestions, they get to Pareto optimal or like dominating solutions. The amazing thing is that we had several of our participants, so I think we had 30 participants. Several of our participants within 10 minutes found solutions that were dominating all the previously known solutions to this problem. So we had AI search this problem for running for weeks over like optimization processes. And within 10 minutes, people just with a local search agent were able to find better solutions that dominated both in terms of benefit. So this was super encouraging. And this was also statistically, so this is kind of the lower the better here. We can see this is the collaborative design, and the human and the AI on their own don't do as well. Interestingly, one of the drawbacks of this is the design diversity also goes down. So in some way, and from what we understand, we don't understand this very well, is that people sort of at some point just trust the AI too much and they don't try wild new ideas pretty quickly if they don't explore on their own. So we already saw that, and we saw one user, but this is sort of over all of our users. We can see that the AI searches much more diverse solutions, whereas when they work together, they actually narrow down their diversity, their design diversity, compared to if they would just work on their own. So this is something to look out for, and also suggest that maybe the AI system should suggest wildly different solutions every once in a while. So since then, we've incorporated the robotic arm, and the robotic arm now I think uses sort of, I think in this study, so I'm not precisely synced about like which, so we've been working on developing the robot AI more and also doing more studies, but I think in this study, the robot was actually searching using genetic algorithms, not just local search. And here we have a robotic arm that not only shows the human possible solutions. And in the previous case, they just saw them on the screen and they could just do them themselves. But the robot actually starts messing with your designs as you're working on to them. So it looks like this. You look at, say, okay, we should put a radar. And this is also, it's a problem that nobody is good at, because nobody has good intuitions about how to design such a satellite. Because you can say, I think I'm going to put this like radar on a dusk dawn orbit satellite that, I don't even understand exactly what that means. So we ran a study where we looked at people working through this problem. So this is what it looks like. The robot's obviously way slow. And then you can see the outcomes. And she says, oh, that's actually a good idea. And so so she says it answers even more questions, but at the same cost. So she likes this specific suggestion of the robot. But I really love this little graph here, which is everybody's like, how did they move through the design space? So here we have 12 participants, and the first 5 minutes are just alone, and then they spend more time with the robot until they say that they're done. They don't want to work with the robot anymore. So the first thing I wanted to notice, which makes this design problem even more difficult, is that people are very, very different when they design. Here you can see just the density of designs that people try out. So participant 7 tried out a lot of things in 5 minutes. So each line here is one design that was tried out. So participant 7 is just like moving stuff around really quickly and just exploring the space. And you can see also that her or his, I don't know, design, like they really explored the design space very broadly. You can see participant 5 started out slow, then stopped and went back to reading about the satellites for a while, then tried a lot of things and then got stuck. And you can see that participant 5 kind of went back and forth between two designs and couldn't figure out how to improve the designs in terms of the science benefit. And again, the interesting thing is just like how different people are, and how really assisting a designer means understanding what type of designer that is. And then look at, the best way to look at this graph is just pick one. So pick, for example, 5 or 7 or 8 or 10. And just look what happens when the robot comes in and how it changes the design and exploration. So it's going to be hard to follow more than one, so just pick one cube. So now the robot is coming in. And you can say, for example, participant 5 is really learning about the design space, moving into more optimal areas. And you can see for some people, and I'm going to stop this here, for participant 7, the robot didn't really help much. They already knew about these types of designs. Participant 5, it was a huge boost to their exploration. And they're very careful. You can see that they like cheap satellites. So they kind of try to stay low. And the robots respected that. So something in the collaboration made them stay on the low-cost Pareto front. So the Pareto front is the sort of trade-off optimal designs. And then, can I move this? Anyway, let's look at another one. So participant 10 was really stuck, very productive, but stuck. But then it just took off. Once the robot came in, they really moved very wide into the design space. So the main things that we learned from this, yes?
Yeah, you said the robot came in. I'm just a little confused. Is the robot doing things or is the person still driving or what's the interaction?
It looks like this. So the robot just starts helping. Yeah. So here the person did this design. So this design is a radar on a dust-down orbit, then a camera on a satellite on a geostationary orbit. And they had this design. It's one possible solution out of 2 to the 60 possible solutions that you have in this space. And this design answers about 10% of all the required questions and costs $5.2 billion to put this in space. This is it's a real world problem. It's a NASA problem. They try to solve this all the time. It doesn't have an optimal solution. It's a lot of negotiation. And this is something that we did as part of helping NASA to try to think about new ways to solve a problem like this, of what satellites to put in space. This is the percentage of of requests they get from scientists. So this answers, like shooting this into space would answer 10% of the current wait list of NASA problems that they want to solve. And it cost them $5.1 billion. And so what is, a better design would be here, right? 13% costing like only $2 billion, that would be a better design. But would this be a better design? Like 3% for $1 billion? So it's not clear, like it's not even, like there isn't a real, this is the simplest, it's a two-dimensional objective space. But in most lectures we have, so what happens here is that we are here, and then the robot says, the robot suggests an additional sensor, and then it calculates that it would solve more of these problems.
That's very helpful. It's answering even more questions.
So it says it answers even more questions with the same cost. So the robot sort of suggested this additional sensor, and this designer is happy with that suggestion. She's like, okay, I'm almost not spending, I'm spending like a little bit more money, and I'm getting, you know, quite a big percentage of additional questions answered. And so what we saw there is what happened once the robot started. So for the robot to learn the human's preferences, the human works on their own for 5 minutes. And then they start working with the robot in exactly this kind of scenario. So again, so we can see participant 5, you know, didn't get very far, but very quickly started solving a lot of science questions. So up to like 20% with about $1 billion launch cost. One of the things we saw when we were analyzing this video with thematic video analysis, and one of the things we saw is that people treat the robot very different. Some people treat the robot as a leader, and I'm not going to play all of these clips, but and they will sort of look at the robot and say, okay, the robot is better at this than me. I'm just going to try and help the robot. I'm going to try and see what it does and try to just like copy that and do it more. And they see themselves as a subordinate to the robot's exploration of the task. And this person, for example, says, you know, the robot, at this point, the robot understands the problem better than I do. So I'm just going to not worry about it. Sorry. Can you hear this?
I guess at this point, the robot's been able to predict it, like, what conditions better than I am. So, like, I'm just kind of trying to help it out in terms of like placement and stuff like that.
And then we have other people who think, just like, keep it there, keep it there. They keep talking to the robot, put it down. They just keep giving commands to the robot. They think the robot should just help them do things faster. And she was very frustrated with the robot. She said the robot wasn't helping at all. She kind of knew what she wanted to do. Also, we saw that generally two types of designers: the tinkering ones who just try to explore as much as possible and learn from it, and the top-down comprehensive designers, which, you know, this one, she was just with the instructions the whole time and just trying to, like, and the tinkering ones felt the robot was too slow for them. Whereas the top-down comprehensive kept saying the robot was too fast. Like, whenever I figured something out, the robot already changed something. So even thus, the pace of the robot is completely different depending on what kind of a designer you are. And over and over again, we saw that people were insulted by the robot. You know, at some point, I felt like I was being dismissive because I didn't know what was wrong or right or how to contribute. And people saw these like very mechanical suggestions as insulting. Other people felt the robot was listening to them, even though it wasn't. The robot did not use speech at all. It just used the current state of the table. But they say it was amazing. Everything I said, the robot immediately took into account and then changed its strategy. So I think the outcome of this particular paper, which was published in Designing Interactive Systems, is that the workspace needs to be managed, especially around turn-taking, in a way that's specific to a designer's requirements. You need to communicate about design goals and respect different design styles. So right now we're trying to build a model of a robot that can actually help people do what they're trying to do. And this is all new, hasn't been published yet, and we're kind of close to, I think, finishing our first paper on this, but I'm really excited about this, and this is also where this project is going. So we are trying to solve the gerrymandering problem. Who knows what the gerrymandering problem is in the US? So you want to kind of create voting districts that are fair, but what even does fair mean, you know? So let's assume that we are not taking sides on what fair means, but we want to help whoever it is who's trying to solve the problem. And so here's an example. This is from 538. This is fair in terms of more votes matter. Right? There's more purple districts, meaning more votes matter. This is fair because it doesn't have weird-shaped districts. Some people say, okay, this district is so weirdly shaped. So this is the least weirdly shaped district in terms of, so is that fair? So we just kind of like, we reduced this after many failed attempts to just 3 possible things you're trying to do. You're either trying to balance the population or minimize the wasted votes or maximize district compactness. And the basic model we're working on here is that whoever's designing is trying a design. This design has certain outcomes on these 3 or more, but in our case, 3 possible metrics. And there's something that causes these outcomes which the person doesn't understand. So the person doesn't quite understand how their changes affect this, but they have a probabilistic model of how when they change something, the outcomes do change. So for example, you can't really predict how purple a district will be just by moving the lines around, but you can learn something about it as you're doing it. And also the person has some kind of objective, like some reward objective, and this is sort of similar to inverse reinforcement learning. And there's a satisfaction, and the robot wants to try to understand, like, what is this? It has some probabilistic relationship between what it sees happening on the table, or in this case, what it sees happening on the outcomes, and what the person is trying to achieve. So one approach is just to have lots of people solve the problem, and we tell them what they should achieve. So we started like that. We said, okay, just try to optimize this outcome, and then we want to see if we can train this with some supervised learning model. So we used the convolutional neural network, but that's not. It could be another supervised learning model. Whether we can try to guess what the person is trying to do. But we didn't get very far because it's very expensive to collect these data sets. I mean, how many people can you get? 100? And that's already took you all year. So we said, let's try another approach. Let's assume that the human is a noisy irrational agent, and let's try to build an agent that's as similar to a human solving the problem, and then use that agent, then train a model of this probability. So let's train a model of the probability of what the human is trying to achieve based on what's happening, based on millions of agents trying to achieve that problem, and see if we can then use that to predict what a human is trying to do when they're coming to the table. So this makes an assumption that the human can be modeled as this epsilon greedy agent. So here's the outcome. So here's kind of where we are with this. So this is an actual person trying to solve this problem. We're seeing what happens on their table. This is what the table looks like. And they can see their objectives. And we tell them, your current task is to balance the population, so try to make this as high as possible, and to regularize the shape, and you don't care about voter efficiency. Go. Like, start moving. Here we can see a person actually like working. Now they're moving the borders around, they're looking at the objectives, and they see how the objectives change. So our question is, can we try to figure out what the person, like, can our agent learn or infer that this is what the person is doing? Does that make sense? And we can see that it's doing not bad at all. So I'm going to start this over. On the right side, you can see the inference. So right now, they think they want to decrease wasted votes and don't care about these 2 others. The right one is that this should be up, and this should be down, and this should be don't care. As you can see, over a few rounds, our model is able to kind of understand what the person is trying to do from just a few moves. It takes a while, you know, because we're looking at these sort of like windows of trajectories. But eventually, our agent does infer that this is kind of the optimal optimization function that the person is trying to solve. So you can see this on a study that we ran. So this is the actual thing they're trying to do, and this is what the agent thought they were trying to do. So we don't have like a really nice diagonal, but we have sort of a diagonal on the confusion matrix. And the big problem here, and I see I'm almost out of time, but the big problem here is that when our agent's trying to solve the problem, so they're trying to, for example, here, trying to decrease the orange one and increase the green one, our AI is very good at this. They can very quickly solve this problem. Here's what it looks like when a human is getting the same task. Try to decrease the orange one and increase the green one. And this is the actual trajectory. This is what the person gets. Like, people are not very good at design optimization. And this is kind of where we are right now. We're trying to understand, is there anything about this, though, that can teach us what they're actually trying to do, and then bring this agent in to help them, solve the problem that they're trying to solve. And now you might say, why don't we just have the agent solve it? Because this is sort of it's a simplified version of the problem. Usually you don't really know what you're trying to solve until you start solving it. And this is another big part of why design optimization is so difficult, because you kind of set your objectives as you're designing something. So you learn about what you could possibly do only once you start working on the problem. And if you've worked on any creative problem, you know this. Like, if you could start over, there's a really nice, like, famous graph that looks at, like, when I talk about design in my class, you do like time, and then you have freedom, and then knowledge. That's like the design paradox. Like, by the time you're done, you know everything you know about the problem, but you don't have any time to do anything anymore. So you're kind of like, and I think this is some of the things we're trying to solve. So this goes until 5, so it means basically I'm out of time. And I didn't talk at all about goosebumps. So maybe let's stop here and take some questions.
So a question, just in the last example, you saying that if you were trying to look just at the right-hand side, right, and inferring from those, which of those design objectives the human is trying to optimize, right?
Yeah. So this is what we can do right now.
Yeah. But the trajectory is very noisy.
Yeah.
Right? So, do you see a signal there? Is there enough to be able to pick up?
So we are. So there is a signal there because in some cases, when like they're doing like a trade-off, like a real trade-off between things, we sort of know that they're trying to improve this, and there's not enough confidence about the other two. But in some cases, when you're just trying to optimize one, if you just would take the one that you think, if you just take the top one, there's enough signal there. This is, I think, about 40 participants, averaging, I think it's averaging so there is a signal there. I would say we're 50% good at this. I mean, we're definitely better than random, and this also, we can calculate that. But so this is a classic example. My student's like, it doesn't work. I'm like, it works. I mean, he's like, well, so my student's ready to throw away this whole project, and I was like, no, we're going to write a paper about this because this is, first of all, super interesting, and second, it's definitely good enough for people to read about. And I think we're learning a lot about what this problem looks like. And one of the things we didn't know was how bad people are. Like, at some point I told him, like, can we just see what people are actually getting? And then he drew this, and we're like, oh, this is really bad. Like, we had no idea that people are so bad at this like 3-objective optimization problem because the bridge from the voting district to like this model is hard for people to conceptualize. Right, and I think we're getting here at, so if I put my philosophy hat on in preparation for the next talk, I think we're getting here at some like really interesting territory when people always talk about like, can machines be creative? Can humans, like, there's something in here. My intuition tells me that this is a good problem to work on. Like, there's something in here that I can't completely formalize, but that really asks some new questions about a human AI or human robot collaboration in the workplace And especially as our workplace is moving more and more towards research and design and moving more and more out of manufacturing. And I think at some point, robots will be good at assisting manufacturing, will be good at assisting logistics, and will be good at assisting warehouse labor. And then we will say, okay, so what we're actually doing is this, and how can I help here? Yeah.
So when you initially introduced like the sort of human robot collaborative design problem, I sort of immediately thought of protein pooling. Are you familiar with that?
Yeah, I'm not very familiar, but I'm familiar at like popular press level familiarity.
There's like a computer program where people who aren't scientists can try to like fold proteins.
Mm-hmm.
And it's like a single objective model. You're just trying to minimize the free energy. But the design space is huge because the protein can have like insane
Yeah.
number of conformations. But so there's the humans who even don't have any like science can do better than machines in some cases. It seems like that might be a really interesting application of this. Because the people who use this program actually like make design scripts to do things like jiggle the protein around once they find a solution to like see if they can make it a little better. And that seems like sort of very similar to what you were trying to do.
Yeah, I think even like a simple approach of like local search around humans' intuition. So the first thing, if I would talk to the popular press, I would say what the AI is doing is looking around, like using the human intuition and using the machine's ability to systematically search around that space. So yeah, I think even that, I don't know if anybody, I would be surprised if people haven't tried that, but I would think that would be useful.
My knowledge of this is about 5 years old, so how does it 5 years ago? I'm not sure where they are right now.
It's interesting. So
DeepMinds has been working on this too.
on this like collaborative.
Well, on protein folding, but
Oh.
they have some new results. They won some competition this year. But I don't know. They're not humans do it, but it'd be interesting.
Yeah, I'm trying to set. So this is a little bit of just like maybe strategic. I'm trying to set our like flag post a little further, knowing that we might not do very well on this because and adding this idea of trade-off objectives and this idea of like you don't have optimality and people have preferences and just because I do think this will work, but I kind of feel like somebody must have done that. Like somebody must have done that, use this because there's a lot of people working on design assistants, like AI design assistants, with these like local search. So the things that's a little bit new about this is the design space is more messy, and we're looking more at these like design trajectories. So most people think about this as like solution and outcome, like a solution and an outcome vector, objective vector. But we're trying to look really at this like trajectory. We're looking at windows of trajectories. So this is why I think there's signal here. Ken, to your question, I think we're actually really looking at like little windows. We're looking at this like a convolutional perspective of like windows of moving between like into and out of solutions. And so it might be that the signal is there because they stayed for a longer time here once this was lower. And then once they came back, they changed too many things around, and then they stayed again for a longer time. So it might be that the signal is in the I would say, well, definitely the signal for us is in the temporal dynamics of it.
The way I'm reading this, it's probably wrong. The thing about it is it's like inverse reinforcement learning where there's
Yeah.
right? They're trying to infer, but the problem is just looking at just the signal. Generally we assume that demonstrations are pretty
Yeah.
consistent. Here they're not at all. They're in a space I'm completely unfamiliar with, right? So
Yeah.
I'm just wondering to what degree you can infer those numbers, that vector 0, -1, 1 from that signal, just looking at the signal alone.
So again, the best I can tell right now is that this is what it infers from 40 signals like that. So we took 40 of these and put them in a chain and took 20 move windows and slid them and used every 20 moves as one data point. So it gets pretty good at one of them. And here's sort of like we're actually doing simultaneously. I don't know if it's a good idea. It might be actually not a good idea, but we're actually both trying to figure out sort of like a regression on how much they care about each objective, and we're trying to also just classify which of the 3 to the 8 possible things they're trying to do.
All I can say is I hope you figure out how to solve this problem before the next election.
Yeah. All right. Thank you.